was trying to invite a slightly different speaker than we usually have, and today we have one. And Professor Michael Robert from Department of Economics. And let me introduce you about him. He joined our university actually a few years back.
2012.
2012, as an associate professor first. Now, a couple of years ago, he's already full professor in our Department of Economics. But he got his PhD from, or bachelor from UC San Diego, and then the master's degree from Montana State, but the PhD from Berkeley. And after that, he joined the faculty from North Carolina State and become eventually associate professor, but then came to Hawaii. So we're happy to have you. And he has a lot of research interests focused on agricultural policy, impact climate change. You will see is a diversity in research. And now he's on the energy, renewable energy, and it's all interdisciplinary in nature. So I'm so happy to have Michael to give us a talk on, I think, a broad spectrum of I think very new to us, but we are very excited to have you, and hopefully we will have more conversations of this seminar in the future.
Okay,
thank you.
Thank you, Vinh. So, yeah, I do kind of a lot of different stuff. These days, I'm mostly interested in looking at the impacts of climate change. And a lot of that's focused on agriculture. And then I'm putting a lot of work in these days into thinking about energy systems and learning a lot about power systems and how our energy demand and as we adopt more renewable supply is linked to weather and climate and how we can balance all of this and make renewables work. So that's involved a lot of collaboration with an engineer. So I do a lot of empirical work, and I'm also doing increasingly a lot of computational modeling on a pretty big scale. I kind of dive into a lot of different literatures. I connect ideas from different fields of economics and like to play and get along with other scientists too, particularly crop scientists in the past. I'm trying to learn power engineering. But I'm not going to talk about the energy stuff too much today. This project, I'm going to talk a little bit more broadly about how economists approach problems from a few different perspectives. There's kind of different camps. And I think this paper is kind of interesting because what we're kind of comparing and combining here are two very different approaches to look at impacts of climate change on agriculture. And it kind of mirrors two different philosophies within economics. So I think that's kind of interesting and maybe helps you get to know a little bit more about how economists do their work. So I'll tell you a little bit of my co-authors here. Noah Braun is actually he started helping us on this work when he was an undergraduate at NC State, and he's an incredible coder. He went to Caltech for his PhD in aerospace engineering, and quite a rock star coder. And he's doing a lot of numerical modeling these days. I think he just finished his PhD. Tom Sinclair is kind of an old guard crop scientist. He's one of the first developers of these big sophisticated dynamic crop models. And a lot of the basic architectures that he's built up kind of drive all crop models these days. But he's kind of has a lot of different skills too. He knows a lot about genetics and basic agronomy and soil science and everything. He's a pretty amazing scientist. David Lavelle is kind of I don't know what happened there, a rock star at Stanford, really incredibly prolific, but he likes to do a lot of empirical work, linking weather to crop outcomes and looking at, and some other things too, but he's very, very empirical. Wolfram Schlenker is one of my closer colleagues, and he's done a bit of work with David as well, but he does a lot of empirical work linking weather to outcomes and then looking at the potential impact of climate change. But we've worked together on quite a few projects, and he's a Colombian. So he's an economist. Dave Lavelle is like an environmental scientist. Tom Sinclair is really a crop scientist, and then an aerospace engineer. Okay, so we know a lot of us are trying to estimate the impacts of climate change, and there's a lot of different ways we try to do this. And it's not just economists, but I'll tell you about the kind of approaches that economists tend to take. The first is what we call an integrated assessment model. And these are really kind of taking a few equations to approximate the entire economy. And it subsumes inside of them usually that the economy is kind of working perfectly in some sense. It's very competitive in some sort of competitive equilibrium. But it's kind of representative agent. It looks like macroeconomics, really. But it's fairly stylized. And then within that, there's these impacts of how rising temperatures or changing climates can affect the productivity of the economy. And then you'll have, the number of people in the economy and all of this. So the most famous of these is this model DICE by Nordhaus, and it's gone through a few iterations. It's kind of interesting if you look at his iterations of the model over time. It started off that there was basically very little impact from climate change. In each generation, the impacts get larger and larger and larger. But that's one kind of school. It's kind of the older school. But now as we get more and more data about just about everything, and economists have gotten more self-critical, I guess, of our stylized models, we want to know the facts. What's really impacting what? And so we're looking for more empirical evidence of what the impacts of climate change will actually be. And these have to make simplifying assumptions, and they're a little bit narrower, but sometimes they're giving us some data. Okay. So the next kind of stylized set of models are these hedonic models, is what we call them in economics. And they are mostly cross-sectional. They're looking across space, different places with different climates. So in agriculture, a pretty famous paper, I think it's pretty much all wrong, but it's pretty famous because it's the first paper to do this in agriculture. It looks at land values, agricultural land values in relation to the climate in a cross-section. And tries to control for other things like soils and prices and stuff like that, or closeness to a city because of urbanization effects, things like that. And links the value to the climate. And there's pretty sophisticated models looking at like home values and wages in different climates. Living in Hawaii is a pretty nice climate, living in the Bay Area, but trying to control for all these other factors and how do people kind of weigh climate in their overall lifestyle decisions. This is pretty messy. And it's pretty easy to find correlations, but do they really imply causation, or is there some kind of missing factor? So that's the error, whatever your model is. So this is usually some kind of regression model that links these values to climate and other things, and then there's everything else. And you get confounding, or you get the wrong implications if the error is correlated with climate in any way. This isn't really a testable thing. So this work has been criticized, and we always keep finding problems. Right? That's why I said that first one was probably wrong. The other problem is that everything affects everything else. When the climate changes, it's not just going to affect one location and hold all else the same, but all places are changing, and there's feedback effects. Now, the integrated assessment model takes all that into account, but it's really oversimplifying a lot of things. This can get a direct effect. You change the climate in one location without changing anything else. What's the value if there's no confounding? But it doesn't take all these feedback effects and kind of the global impacts into account either. So it's very narrow and probably confounded. So we've become a lot more skeptical of these, and we don't see as much of these published anymore. So the next generation of impact models really kind of aligns with the modern fashion in economics, which is really built up over the last 20 years, which is really looking for natural experiments. where you have really compelling, we call it a source of identification, where you have some variability in something that you can really defend as truly exogenous, as if it's an experiment. So this is really, to get into the top journals today, you gotta have that. And so everyone wants to do climate change work because they think weather's pretty exogenous, weather's pretty random. And the same, if I look at the weather on this day today versus this day last year, you probably couldn't have forecasted it at least a year ago. And the difference is pretty exogenous, as if random. And why would it be correlated with other confounding factors? So people thought this, well, compared to most economic variables, this is pretty exogenous. We care about weather and climate and how changes in this are going to affect things. So we think that this is a weather anomaly of some kind. Is going to be pretty exogenous and not correlated with other factors. There can be problems with that too. In some cases, maybe I'll get into that a little, but at least in some contexts that can be okay. Usually these models, they center everything on location using the jargon, you'll hear fixed effects. That's really just centering your data so you're only looking at anomalies in value or some kind of outcome and anomalies in the weather. And then, of course, change in weather is not the same as the change in climate. And people can adapt, and there can be other things, and there's going to be all these prices and other sort of feedback effects. This still ignores all of that most of the time. So it's still very narrow and fairly limited in some ways, but at least some of these regressions are a lot more stable. They really look causal. You can make predictions out of sample. They certainly, they're probably more defensible, and some of them are than others. So this tends to be the way things are going. So weathers are really random. So here's a pretty nice review of this literature by Carlton and Sean. Solomon Sean is turning into quite a superstar these days. He's gets in the press a lot. He was actually a postdoc of mine for a little while. We never finished that project. But so this is the work that I'm most well known for. It's one of the first papers that was up here, where we link weather to crop outcomes in kind of a clever way, we think. And it found this really, this is kind of showing this log of maize yield in relation to temperatures. And you see not much of a relationship, maybe a slight upward thing, and then it falls off a cliff when you get temperatures above around 30 degrees Celsius. The more you get above that, yields really fall pretty fast. And so this sensitivity to extremes meant that if you shift the temperature distribution to the right, yields could really fall off a cliff. And that was really not what people were focusing on when they were looking at climate change impacts. They focused more on precipitation and length of the growing season, both of which were looking pretty good. Sensitivity of extreme heat is not something that really fits into a crop model. So it really kind of, some people didn't really like this. In the crop science literature, we've been trying to figure out what is that extreme heat effect, but it's incredibly robust. You find it over different decades at different locations in a lot of different cases. So people started using this technique and linking it to all kinds of outcomes besides crops. Yeah?
Is that temperature average over the growing season, or is this incidence? Short periods of time.
It's incidence, and that was what was kind of neat about this. So people had done regressions like that where they would take like average temperature, but if you take average temperature, it kind of blows out all the extremes.
Right.
So this was really a lot of hard work in data interpolation to get good estimates for exposure for each crop. So we had a whole distribution, and then we cross-multiplied the frequency distribution of temperatures with a design matrix for these different types of spline curves, different ways you could estimate a curve. So it's a different way of using the data. And it's a little bit more work, but it allows you to recover this kind of relationship, and you wouldn't see it in average temperature. It would just be kind of a quadratic kind of smooth relationship. And it smooths out the extremes. So you couldn't see that without doing that. So more of the work, some of these things just use quadratics. like that. But more and more people are starting to take that whole distribution into account, and then you're starting to see these effects of extremes. And that there's been a lot more focus on that by the IPCC. And well, Chris Field kind of wrote a big report. He's coming here on Friday. And in geography. He's like one of the most famous scientists in the world these days. You might want to see his talk. Anyway, so there's a lot of these effects here, but I don't know why that turns off. A few of these look at mortality, right? You get more mortality when it's cold and when it's really hot. This is one that's showing mortality in India. You get more mortality up here. A recent paper, Carlton actually came out with a paper after this one more recently. It might have been this year or late last year. Looked that suicides really go up in India when you get extreme heat. And it looks like it's bad agricultural outcomes, and there's suicides associated with that. So civil conflict, migration, total factor productivity. That's just kind of a productivity measure. So a lot of different stuff. Okay, so econometrics is really data analysis and economics. It's just statistics. There's a couple different approaches. You might see this too in different fields. But we call it a structural approach. The structural approach is to basically derive some equilibrium conditions about how people are going to behave, firms, what they're going to produce, and how people are going to buy things, and what everyone's going to do. And there's going to be some sort of equilibrium. And there's parameters that drive that. And then we calibrate all the parameters by fitting it to data, and then trying to see what happens. So this is what we call a structural approach. We kind of have a model for how things are supposed to work, and then calibrate that with data. Design-based approach is different, and this is much more fashionable these days. There's been a big real trend from the structural approach to the design-based approach, because here everyone was worried about confounding and all of that. You don't really have an experiment that's identifying this thing. So the design-based approach is to use an experiment of some kind, a natural experiment, a big policy change, some kind of, there's basically a handful of tools that we use. But finding some kind of as-if random variation to identify a relationship. And so weather's the real candidate here. So I think the structural approach is a lot like a crop model. A crop model, I don't know if you know much about these things, but they're really just mathematical models of how a plant grows. And it's a dynamical process where the plant has a little bit of stored energy, and it starts to grow. It has leaves that are a certain size. It gets solar radiation, nitrogen, and water, and it grows a little more. And so the energy gets put into growth of the plant until it gets to a certain stage, and then the energy that it gets from its leaves then starts being put into the seed formation and growth. And then whatever that energy is stored at the end of the life cycle of the plant is the yield. So it's just a dynamical model of the physiological growth. And you can test certain features of this model in the laboratory, but putting the whole thing together is a different story. And there's often things that are set outside of the plant growth model, like a pest infestation, that kind of upset those dynamics. And maybe you don't measure the weather just right. And of course, any error that you have would compound. But a lot of the specifics of these things work pretty well. So this is Tom Sinclair's kind of classic model. It doesn't model the soil moisture, the water balance. So you have to add water balance to this particular model to get there. This is kind of the basics. There's a few books out there where you can read about all this stuff, but it's, when you code this thing, this is what we did. We coded this, converted it from Fortran to R so we could really understand what was going on. And it makes some sense, and learn a little bit about photosynthesis by doing it. And this is our model. This is like different functional forms that you can fit. And here's the temperature distribution. This is taking into account variations over time and over space where they grow all the corn in the United States. And these are the links between kind of instantaneous temperature measured on a daily time scale. It could be a fraction of the day, but that's just kind of the units that we're using, and then log yields. So this is one approach. You can change the weather on this model and see what happens to how it affects yield. And that's what Rosenzweig and some of the earlier research looking at climate change impacts on agriculture would use. Or you can use a statistical model like this, and you can change the weather and see what happens to yield. And these are kind of the two basic approaches to looking at what could happen in climate change. And there's been a lot of debate, well, how similar are these models? And now there's lots of different people with different crop models, and there's different statistical models, and they're trying to start making comparisons between them. A lot of these comparisons, though, use experimental field trial data, which is different than farmer data, and what farmers actually do on the field, and the number of plots is pretty small. And so sometimes they compare a lot of models, but there's only so many data points. And if you know anything about crop yields, you'll know that they're incredibly variable. Wild variability over even a small geographic space. So you need a ton of data to really have confidence in any kind of pattern that you're finding. So David Lavelle is pretty optimistic based on some of these things, because he thinks we're getting towards convergence, that if we average the models, we do pretty well and things like that. But I'm a little worried that a lot of the comparisons that have been done so far, while it's great they're getting more models and they're starting to do these intercomparison projects, I think it's a fantastic direction. The number of data points for most of it is pretty small. So we're just going to compare two very simple models. We don't have all of the models, but we're going to do the other thing. We're going to take tons of fields and we're going to use farmer fields, actual farmer fields. So anyway, a little bit about crop models, the strengths and weaknesses of them. Based on the fundamental physics of biology, underlying photosynthesis and plant development, the statistical models are kind of ad hoc, right? We don't really know what's driving what. Some assumptions can be rigorously tested. The weaknesses, there's limited climatic and geographic scope of experiments relative to the scale of uncertainty. So, a lot of this stuff is done in a laboratory and under very controlled conditions, and in the real world, it's not like that. Like some of this stuff, some of the early work that suggested CO2 would increase, CO2 fertilization would increase yields by 50%. Well, that's probably true in a nicely controlled greenhouse, but it's different when you're out in the field. And so now optimism's changed considerably as there's much more complicated dynamics out in the field. It changes the temperatures and the canopy and all these other weird feedback effects. So it's not quite the same. So, and economists, of course, this is really dear to economists. Farmer behavior really matters. And a farmer is not going to manage his plants the same way a scientist would in an experimental field plot. So a statistical model, we have strengths here. We have a lot more data. We can take observational data from lots of places. We've got really good data from the US Department of Agriculture that goes way back, that appears to be pretty darn accurate at the county level. There's a lot of fields there. The farmer behavior, we don't know exactly what they're doing, but it's implicit, right? We see an outcome that's a combination of the weather that was there and then all the actions that they took, the inputs that they used, how they managed their crop, and so on. Weather variation presents a pretty compelling natural experiment. It's pretty darn exogenous from one year to the next, and we can kind of control for technology in other ways. Weaknesses, it still is observational data. It's still not experimental. It's not bad as far as quasi-experiments go, but it's still observational. The mechanism is obscured. We don't really know what creates this link. So even if we can claim that this is a causal link, what creates that causal link is not clear. Inference about adaptation requires stronger identifying assumptions. So changing the climate is not the same as changing the weather. One of the interesting things about this relationship, and I think the most interesting thing about it, this nonlinear relationship, is if we look at the pure cross-section, which would take me a while to explain, I'll skip that, versus the pure time series, looking over time, you get the exact same relationship. Not exactly the same, but statistically, they're not differentiable, and they give you almost identical climate change predictions, which is pretty astonishing, I think. and it gives you this kind of distinct, strange, nonlinear relationship in both directions. And so while the cross-section could be confounded, it would be very odd that it would be confounded in a way that would give you that same relationship. So it suggests that there's limited scope for adaptation, and that this is actually causal and probably indicative of what we get with climate change. So to me, that was the most powerful aspect of that paper, but I don't think that's what people see in it. But anyway. Okay, so this paper, we've got field level data. Unfortunately, we don't have access to this data anymore, but at least we got a couple papers out of it. This is a really amazing data set that we were lucky to have access to for a while. It's field level data on the large majority of actual fields of farmers in the United States. It comes from the Risk Management Agency, the USDA. Those fields are insured through subsidized insurance. And we have the yield outcome, we have the planting date, we have the lat and long location of the field. And we know how big the field is and all this other stuff. So it's a pretty remarkable data set. Millions and millions and millions and millions of observations. Actually, we have to sample from it because it's so big. So we sample 100 fields in each county and each year for 12 states, and we merge it with, this is actually a super nice version of PRISM that you have to pay a ton of money for. USDA paid for that. We didn't pay for it. Most of the data that we use for this kind of stuff, it's the 4-kilometer daily data, and we did some of our interpolation ourselves. We used weather stations and their 4-kilometer monthly data, and then we do a lot of stuff to downscale that to daily data, and then we fit some sine curves between the min and max to get time at each degree within each day in each 4-kilometer grid cell. But here we do something similar, but we use their actual data on an 800-meter scale, and we use the min and the max, and we interpolate between them to get estimates of temperatures in each hour. We use daily, the crop model takes daily precipitation, and we match the grid with, we just see which grid each field falls into, and we match that. That's kind of expensive, linking all of that. We compare the model outcomes, so we run a crop model for each field based on the planting date and the weather. We feed the weather in, and we assume that they have plenty of nitrogen and there's nothing else limiting growth in that field. So the simulated yield is going to be higher than the actual yield, because anything that we don't observe can only knock that yield down. This is almost like yield potential. So we take the model outcomes, the actual outcomes, and then we develop some statistical models that include the prediction variables that we've used in the past for our statistical models, plus the model yield. So we kind of combine them. How can we improve predictions by putting both in there? And then we allow finally for interactions of all these things. And I think if you were to use machine learning or some of these neural networks or fancy techniques, I'm pretty sure you could do a lot better than what we do here. But the predictions here are actually pretty darn good based on things that I've seen in other locations. I didn't go into an exhaustive, I didn't go into that in a lot of depth, but based on what I've seen in other literatures, this is predicting outcomes pretty darn well. And then we look at climate change predictions from the crop model, from the statistical model, and then from the combined model. How do these different approaches give you different implications if you were to shift the weather, make it a couple degrees warmer, or change precipitation or something like that uniformly? How does that change the outcome of using these different approaches? Okay, so that's kind of what we're doing, and I'm going to just show you a bunch of results. Any questions at this point about the whole approach? Okay, so the crop model is based on this kind of classic by Bouchow, Sinclair, and Bennett in the Agronomy Journal in 1990. The inputs are daily min and max temperature, daily solar radiation. We got that from NASA, kind of 1 degree, maybe it's a ½ degree grid over the planet. Daily rainfall, and the temperatures come from the PRISM data, and rainfall comes from the PRISM data. We're always assuming deep soil. So if you were really to push this, you'd want soil depth, which is kind of a key parameter in the crop model, to really depend on the specific location. And there are some databases. We did try this to some extent, but this really wasn't helping our predictions very much. It was really hard to calibrate this well, and we were finding we were doing pretty well by just keeping it one deep soil base. And that's pretty true for most of the Corn Belt, really deep soils. So just to keep it simple, as the first one, we just keep it deep for the whole, for all fields. And then we fix these radiation use efficiency and water use efficiency parameters. One of the interesting things about climate change and CO2 fertilization is that higher CO2 can increase water use efficiency, which might actually increase drought tolerance, and this might be one of the more interesting compensating effects from climate change. Again, this is a hard thing to do empirically because we just kind of have a smooth increasing trend in CO2. Using observation data to do that is kind of tough, but this is what the experimental evidence suggests. And then we have a fixed maturity parameter. Farmers will actually, they'll pick a different variety of seed depending upon when they plant. Because if they have a shorter season, they'll want something that matures more quickly. If they have a longer season, they'll use something that matures more slowly. And the longer the season, the higher the yield, because the more solar radiation that you can collect during that time period. So we don't observe that, but that's a critical choice by the farmers, is which variety and what rate of maturity do you use. That's kind of a key aspect of how the crop science is growing yields over time. So the key variables in our simple regression we use, and the thresholds in this are all determined to maximize fit based on earlier work. We just fixed them here. And it's the piecewise linear function where you get a little bit up and then the sharp down. And you can capture that effect by using growing degree days, which captures temperatures between 10 degrees Celsius and everything above 10 degrees Celsius. And you take the minimum of the temperature minus 10 degrees, the lower bound, or 19. So at 29 degrees Celsius, anything above that just gets a 19. So it's bounded at 19. And then you multiply that by the frequency distribution of temperatures. Okay, so you integrate that over the whole growing season, where this is a continuous approximation of the continuous distribution of temperatures. That's growing degree days. And then we have HDD, or high degree days. This is the extreme heat effect, which captures temperatures starting at 29 degrees. So T minus 29 times the frequency distribution. Everything below 29 is thrown out. So this is just capturing the upper leg. And then we have total growing season precipitation. We've done different versions of precipitation, but the high frequency interaction between temperatures and rainfall really matter, but a simple statistical model is going to capture that. The crop model captures that. That captures the water balance and that timing effect. It's very hard to capture that in a simple regression model. It's hard in a simple model to do anything that does better than just precipitation and precipitation squared for the whole growing season. We've tried lots of other stuff. Maybe someone will come up with a more clever specification. But that's all this is. It's these two variables, p and p squared, and this is just accuracy. So what do? So we have our simple pooled regressions. We have the natural log of the actual yield in relation to the model yield. So this is the crop model, and the crop model squared. So what this is going to do is we're going to kind of recalibrate the model yields, because they're always going to overpredict the actual outcome, and we know why. So we want to use this as guidance for actual yields. We should probably center it based on actual outcomes. So that's what we do. So that's the crop model. The statistical model, this is it, the log of actual yields. There's growing degree days, high degree days, precipitation squared. We also have a time trend in here to account for technological change. And then we have our errors. And the combined model puts all of these things into one, and you predict the outcome. And then we also have some models with fixed effects. We're going to center everything. so that we're going to basically remove the mean for all of the explanatory variables and the dependent variable for each county. So you're centering everything on each county. So you're not making comparisons across counties, you're only making comparisons within a county and identifying based on changes in weather within a county over time. Okay, so this can get rid of some of the potential confounding that you might have because soils are different in Iowa versus Missouri. Okay, so it washes that stuff out. So that's what this does. The other thing we're going to do, so to see this, there's the AC has a different intercept for every county, and then we also add sigma S, so we're going to have a different trend for every county, so you can have different technological change in different states actually, as sigma S. So each state gets its own trend. So it's a little bit more, but otherwise it's the same. We also do these emulator regressions, where we make the dependent variable the crop model. The dependent variable is the crop model, and the explanatory variables are our statistical variables. So if you were to approximate or summarize the crop model with just these aggregate statistics, what would you get? And what's the relationship, what's that relationship? What do these coefficients look like versus when we put actual yields on this side? And that's kind of interesting. Okay, so then we have these statistical tests. They're called non-nested J-tests that really allow you to test whether one model's better than the other or whether you really need to have both. Whether there's statistically an improvement by including both. We do some data cleaning. We get rid of extremes and things that are implausible. We also make counties. Some of these counties, we're really focused on non-irrigated agriculture, which is most of the corn belt, most of the corn. But in west of the 100th meridian on the mainland, most everything is irrigated. And that's going to, of course, be a different dynamical relationship that's not appropriate for this. So we throw out all the irrigated fields. So we omit counties with fewer than 400 combined observations. Most of those that wouldn't have, that have less than that is because they're mostly irrigated. We wanted to make sure we had a critical mass of non-irrigated. So at the end of the day, we have 1.12 million observations in 741 counties over 18 years, spanning roughly the mid-90s to 2012. So, is this pretty representative? We think so. This is a scatter plot done with shading because there's over 1 million observations. We can't show you every point. That this is a 45-degree line. This is the NASS county level yield, and this is the average of our sampled fields. So it looks pretty darn good. There are some outliers down here. These are some of the counties that have a mix of irrigated and non-irrigated fields, but since we're only looking at the non-irrigated fields, they tend to be lower yielding than the county is an average. And so that's why we get that. But this shows a regression of one on the other. This shows you, each of these box plots has, about, how many years did I say? 18 times, well, let's see, there's about 100 counties, about 1,000 observations per year per state. So one of these box plots is about 1,000 observations. And this shows the actual yields and the model simulated yields. And you can kind of see they kind of go up and down together, but the model yields are, of course, a lot higher. But the other thing I want you to really notice is that incredible spread. Within a state, within a year, huge variation in yield outcomes. And so this is why I'm a little worried about these studies that have, 20, 30 experimental field plots. I don't know if that's enough to really get a sense of how these other models are working. So we got 1,000, you don't have as many models, but we got 1,000 data points per year per state. Here's a couple more. We've got like 12 states, but I just showed you a few of them. And some are more variable than others. Kansas is perhaps the most variable. Kansas and Nebraska. This is getting a little bit more west. It's a little drier. You had a
And
question?
these data are exclusively for maize, right? That's the only crop you're looking at.
Yeah, today I am, yes. We get pretty similar relationships for soybeans. It gets pretty messy looking at other crops, particularly wheat, because it's so different in different locations. And we've got so much data for those two. So we've done a lot of our work on corn and soybeans. They're also the two biggest crops in the United States and pretty critical for world agriculture and world commodity markets. Okay, so this is just some correlations that shows the actual numbers. These are the actual versus actual. This is the model versus actual yield, a correlation of 0.39. This isn't the whole sample. You can see a stronger negative correlation with actual and high temperatures. You also see that pretty similar strong correlation between the model yield and high temperatures. And then this is kind of an interesting contrast. If you look at the model yield in relation to precipitation, you get a really strong correlation, but it's a lot weaker with the actual yields. So I guess the strongest relationship here is right here. Precipitation and the model yield gives you 0.72, but only 0.22 is the correlation if you look at actual and precipitation. Pretty wild difference. And this when we first came out with this stuff showing the importance of extreme heat, this wasn't what they expected. They really thought that and these are simple correlations. They're not conditional on the other variables. Right? But these guys were thinking, the crop scientists were thinking precipitation is everything. It's different in different locations, but in all cases, the model yield and precipitation is really, really strong, but the actual yield is actually pretty weak. And in the hot, dry areas, you get this really strong negative relationship for both, but these things do get pretty weak when you get in cooler states. Here's a correlation between the fitted and the actual yields for the statistical model, the crop model, and the combined model. So we're doing pretty badly, actually, in the cooler areas. We're not predicting very well, but we're predicting pretty good in the areas that can get pretty hot and dry. The places that do experience really bigger swings and get more drought. And that's true with all of the models. So this is the statistical model, the crop model, combined model, and these are with fixed effects, and these are without fixed effects, essentially. But pretty similar correlations. The crop model is actually doing a little bit better, and I'll show you that. If you just do these, they're fairly similar in terms of fit overall, but the crop model does better, the combined model does a little bit better still. When you include all these interactions, you do even better than that. So this is kind of a correlation between the statistical model, here's the actual and predicted, and the process model, you get these, well, the process model is deterministic. I think it's kind of amazing that the process model does this well. It's pretty impressive for the crop scientists, I think. The actual versus predicted, because you have this kind of yields, you just kind of have this hard relationship over here. Here's the combined model. It's a little bit stronger and a little bit nicer shape. And then this plots the process model against the statistical model. So the models have a correlation of about 0.62. So they're saying fairly similar things, the two models. Okay, so if we add fixed effects, the correlations go up. And they also have the correlations actually mean something because they have, well, my first stats prof said you have to have a nice football shape to your correlation plot for the correlation to really mean something. And these kind of have that nice relationship. And then with fixed effects, the correlation between the models is actually quite high. They're saying fairly similar things. So all this looks like one thing. Now, this kind of surprised me after we looked at the models, and they're saying kind of the same thing. But then we started looking at climate change impacts, and then that kind of surprised us. Okay, so anyway, I'll show you some tables. Let's look at a couple of the pieces. So here's our explanatory variables, the process model, the log of the model, the log squared. I divide the coefficients by 1,000 because they get kind of small to boost them up. And then I divide these coefficients by 1,000 just to get the scale, so now it doesn't have a lot of zeros. And this gives the adjusted R squared. So here's just the process model, and the fit is 0.174. That's a little bit better than the statistical model. And then the combined model goes up to 0.23 when you put these things in. The one thing that's kind of interesting here, you have, even when you put in the, I want you to put in the combined model, we have the process model here. And these coefficients aren't too different, but this extreme heat is still coming in even after we include the process model. So there's something about the heat that still comes in, the process model is not capturing. And this is the T-stat, -7. So it's very significant, even with kind of clustered, robust standard errors. So very significant extreme heat effect conditional on the crop model, and this is our first sort of warning that something interesting might happen here with climate change impacts. This is the same kind of thing with fixed effects. The size and significance go down a little bit, but this is still coming in, and it's a little bit less severe than if you just have the crop model, or you just have the statistical model, but even after you add the process model, this is still a pretty big and very significant effect of extreme heat. So the process model isn't capturing all of that. The other thing that we wanted to look at, so this is the emulator. So the dependent variable now is the process model yield. The process model yield and the coefficients here, the relationship with precipitation is very similar to actual yield. If we had actual yield, here is the dependent variable, we get very similar coefficients here. So it's the same kind of relationship with precipitation, but these coefficients now are -1.5. So much smaller than the coefficients here, which are -3, -4. So, and this is actually conditional on the process model. So there's something about the heat. There's something about the extreme heat that's still there. Okay, so the J-tests, these tests, I don't want to spend too much time on this so I can get to the end, but basically it says you need both models. They both have something that the other's missing. Okay. And this shows the relationship of extreme heat conditional on precipitation. These are just predictions from the models. And the fit with extreme heat, with the process model, statistical model, and the combined model. And of course, you get this much sharper relationship with extreme heat conditional on precipitation. So controlling for everything else. And if you add the fixed effects in, you also still get a steeper relationship with extreme heat on predictions conditional on everything else except that. So this is out of sample predictions to really assess the models. What we do is we remove 1 year at a time across all counties. Remove the entire, because there's a lot of correlation within a year, right, with the weather. We remove a whole year, use the remaining years to estimate all the models, and then we predict the year we left out. And we do that for all years. So this kind of cross-validation to take into account the spatial correlation. And we do this for all the years and then make predictions for the year we left out for all the years. And this is what we get. This is the correlation, the field level correlation between actuals and predictions. And so there's the models without fixed effects and the models with. The full model is just a more complex combination of the process model and statistical model. I didn't show you coefficients from that because they're basically impossible to interpret. You have to spend a lot of time to do that. But if you add richer interactions between the variables and the process model predictions, you get better predictions. And that's what always predicts the best. But if you look at just the raw models, here's the in-sample fitted values and the out-of-sample values. The process model is beating the statistical model a little bit by a couple points. And then the combined model does bump up a bit. With fixed effects, it doesn't bump up quite as much, but these are statistically significant improvements from out of sample. Now, and we looked at 2011 and 2012 because they're kind of unusual years. If you're paying attention, 2012 was a crazy bad drought year. It was the worst drought that we had since at least the 80s and possibly since the Dust Bowl years. It was really, really bad. So that's kind of interesting because in the really hot years, the statistical model does a lot better. In the really bad years, statistical model does better, but on average, the process model does better. So when extremes happen, the statistical model does better on those. The process model does better on a kind of a case-by-case basis because it's probably getting the water balance and the temporal pattern of rainfall and radiation and all of that. It's doing a better job of that than the statistical model because it's just not taking that into account. So that's the way I sort of interpret all of this. Okay, so let's look at the climate change predictions. We're going to look at, we had 5 scenarios. I'm really only going to show you 3. We have the baseline, then we add 2 degrees to all temperatures over the whole distribution. We add and subtract 20% rainfall. And we look at just rainfall measures, so we can kind of unpack how much of this is rainfall, how much is temperature changes, and how much is both. Most of these things look about like you would expect, but what's kind of interesting is the extreme heat effect goes up quite a lot. This is kind of a key impact from climate change because of this kind of threshold effect. So the baseline versus adding 2 degrees Celsius, you get a pretty big bump in that variable. Okay, so what do the impacts look like? This is the stat model. If you just increase 2 degrees Celsius, you get a decline of about 20% in the statistical model. If you increase temperatures and increase precipitation a little bit, by about 20%, you get a hit. It's not quite as bad, but it's about -17 or 18%. But if you use if you increase precipitation, you get an increase. The process model, you get much smaller impacts with the temperature increase. If you increase both, you get a mild increase. And if you just increase precipitation, you get a big increase. The combined model looks a lot more like the stat model because it's picking up the effects of extreme heat. And the full model, where we allow for all these rich interactions, even more precipitation is bad. But it's otherwise pretty similar to these others. So fairly different implications for climate change. But in fixed effects, it doesn't make that much of a difference, which isn't always the case in this business, but this is pretty similar. One other thing that's pretty interesting is the fixed effects are only looking then, again, within a county, where these effects look both across regions as well as within counties. So this is kind of including differences in climate as well as differences in weather, where this is only looking at differences in weather. And the effects, when you're only looking at weather, are less than the effects when you look at climate as well. So again, I think it's not rock solid evidence, but it's very suggestive that climate change doesn't look good. That with adaptation, if you will, impacts are not diminished like you'd expect. Okay, so this just kind of shows the spatial pattern of impacts. The statistical model and the combined model, you get this bad stuff in most of the Corn Belt, but it looks good in the crop model. Okay, so some conclusions. If you give me a minute, I'll show you a little bit about what Jimmy's doing, which I think is really neat relative to what you guys are interested in. Anyway, total rainfall is a much stronger predictor of modeled yield than actual yield. Extreme heat is a stronger predictor of actual yield than modeled yield, especially conditional on rainfall. Despite the above differences, the models perform with similar accuracy and have similar geographic strengths and weaknesses. A combined model has significantly improved prediction, mainly due to additional extreme heat effects. Damages under climate change are much less severe under the crop model as compared to the statistical model or combined model. Models with fixed effects have similar or less severe impacts from climate change, which suggests a limited scope for adaptation. Anyway, I'm a little more humble these days about what all this really means, these impacts. If you look at, one of the other kind of interesting things is we haven't really seen big impacts in the United States from climate change so far because this extreme heat is actually, the incidence of it has fallen a lot in the Midwest during the summers. So despite the fact that we've been getting global warming around much of the world, the extreme heat's actually increased in most parts of the world. In this big breadbasket of the United States, we've had actually an incredible decline in incidence of extreme heat, except for 2012. Aside from that, it's been really good weather. And so I sort of feel like we've gotten lucky so far. Or climate change is doing something strange in the Midwest. I've talked with some climate scientists about this. They call it the warning hole. So fascinating stuff. I'd love to talk with you guys about it. Anyway, I want to tell you, so a lot of behaviors affected by extremes, particularly energy use, and there's been some, it's only fairly recent that economists started doing this. I have a pretty good colleague at Berkeley, Max Offhammer, who's gotten a few papers out recently looking at this. I have a colleague who's been doing this in Hawaii, one of our grad students. We haven't published it yet. But you get these U-shaped relationships with temperature. You know, we use a lot of energy when it's hot and when it's really cold for air conditioning and heating. But the relationships are a little different. Coal tends to be a base load power plant, so it's kind of always going on. And then gas and oil tend to be the things that respond when you get peaks. And so these things really spike when temperatures go up. So this is kind of behavioral response, but how do emissions and the atmosphere and the weather interact to create pollution outcomes? We saw these mortality effects from climate. Mortality is linked to temperatures, and people say, well, that's exogenous. Temperatures go up, we're seeing more people die, this is a bad impact from climate change. How much of that's pollution? And how do the temperatures and the nature of the atmospheric change interact with the emissions to create pollution? And that can be a much more complicated process that I don't really understand, but you guys might know a little bit about it. So I think these things need to be combined, and Jimmy's starting to try to look at this empirically, looking at links between emissions and temperatures, and then looking at pollution outcomes in relation to temperatures and emissions. So that, and not just temperatures, but other aspects of the climate and winds and directions. So it gets pretty complicated pretty quickly. But I think a lot of that would be aided by people who know a little bit more about atmospheric science than we do. So this is kind of on the emissions side. This is what's going on with the power plants, and then this looks at the link between ozone and temperatures, just kind of reduced form. I don't know, does this have like
This is surface ozone, yeah. This is ozone here, where we look.
This is where people live,
Yeah.
and the emissions are at different locations, so kind of linking all of where the emissions take place and where the people are. And this kind of takes this into account. I mean, it's taking into account where the people are and looking at the temperatures in those locations. Or maybe it's, I don't know exactly how, there's a few different ways I think it's done this, but there's PM 2.5 and ozone, two of the major links, and you're seeing these really strong links with temperatures anyways. This seems to be the clearest signal again, but these complex interactions I think are pretty darn interesting, and would be a good place to push. Because, as I was telling Feifei earlier, in environmental economics, the predominant focus is on mortality effects because they dominate cost-benefit analyses at the EPA or anywhere else. Anytime you start putting numbers down, when you put the value of statistical life down, it just blows everything else out of the water. It's very hard. It's just going to dominate any cost-benefit analysis. So there's more and more attention on that. And since we're seeing mortality effects from pollution, and we're seeing mortality effects from temperatures, this is really critical to all climate change impact studies that aren't, you know, the integrated assessment models, but I think even to some extent those now. It's all driven by mortality effects, but mortality effects and pollution, both of these are big effects, and they're all interrelated. And I don't think we understand those interactions very well. So I think it's probably a really important place to push. But but I haven't done much. Jimmy's doing all the hard work.